I don't know what this data proves yet, but 10 measurements, all taken with their respective solar noon from different places, should all point to the same sun, or they shouldn't. If they don't, then something is wrong with the heliocentric globe Earth model. So let's test it. On March 21st and 22nd of this year, 2026, right by the equinoxes, a group of us recreated one of the oldest experiments in history, the Eratosthenes experiment. Same idea. Sticks in the ground, measure the shadow, do it at solar noon. We had 9 people take 10 different measurements. Most of us with the same apparatus, this one here. We were all at different locations across the contiguous United States as represented by these orange lines. The key rule, everyone measures at the same moment to them, solar noon. Because if the sun is far away, those angles should line up in a very specific way. All this data is public, no filtering, no hiding edits, no paywall for the truth like some con men like to do. You can run these numbers yourself. Also, asked a number of flat earthers, 2 said they'll do it, and one of them actually took a measurement. So this isn't one-sided data. So this is the data set. As you can see, latitudes are to 0.1 degree. This is the angle of the shadows. And these are all pictures of everyone's measurement, like this. There are a few caveats. This person here used a different apparatus. We wanted to test if we could do this again where not everyone needed a 3D printer. This one here says 15 degrees. That's definitely not accurate. I think it was around 55 degrees. That's why I have that note there. You can look at this picture and be the judge of it. And the last thing is when I made my design, I measured, these are all the angles, and I measured from the center of the pole, but the shadow is being caused by the edge of the pole. So every measurement is slightly off. I came to somewhere between 1/4 and 1/2 degree. So down here, I kind of took a rough average and adjusted them all by 0.3 degrees. You don't have to do that if you want to use this data for whatever you want, but that's what I did. So I'm going to use Desmos to map this. Here is Earth. We're going to make it a 2D model to make it easier to visualize. The radius is 369 miles. So we plugged everybody into the table here, and then this formula, cosine moves the point left and right, sine moves the point up and down, and it lines up with where their latitudes should be on Earth. So every measurement has a real position. Now with ChatGPT's help, I got this formula, and this is basically drawing a line at the angle based on the tangent of that pinpoint. And as you can see, most of these lines are pretty close to parallel. We have these two up here converging. We've got 15 shooting way down here. We do have outliers as expected. We are humans and we're using a really crude, simply printed device, but the pattern's pretty clear. They're relatively parallel. So now we'll do it with flat Earth. This point here is Polaris. This is the North Pole. This line here is the equator. We know from the North Pole to the equator is 6,215 miles. So I just put that there and drew a straight line. That is the line that the sun was above that day. Now we've plot each observer based on their distance from the equator. This is a distance anyone can travel and measure. You could take the drive if you wanted to, that's going to be a pain, or take a plane, whatever you want, but that is based off of 69.056 miles per degree. Now we draw the lines. If the sun is local, these lines should all intersect or be very close to intersecting at the same exact point above the equator. And we have the 15 degrees shooting way south. What we do is zoom out. We get a number of them intersecting way short of the equator, a number of them intersecting a little short of the equator, and one of them intersecting, it looks like, past the equator. But when we look at this, these should all be pointing at the same point or really close to the same point, but they are not. The sun is here apparently about 700 miles north of its actual position. So the intersection points are pretty much all over the place. But let's put some numbers in and just see. If we're going to ignore this one down here, but if we take these intersecting points where the highest and the lowest ones intersect, 3140 and 3559, that's a spread of a little over 400 miles. So for this model to work, the sun wouldn't be a small point. It would have to physically span 400 miles diameter and be sitting, it looks like, about 3,400 miles high for all these angles to intersect at once. That's something that's not observed, not measured. Now let's head back to the globe. What we are told is the sun is 93 million miles away about. So what we're going to do is expand these lines out and put the sun out 93 million miles. There we go. That is pretty much to scale. And let's look at where these lines intersect. So we've got 15. We've got 15 way down there. But all of these ones that are relatively accurate, we'll look at. So it looks like if we zoom in here, we can see that this is a single line. This is 2 lines. And this one here is 2 lines. So it looks like out of our 10 measurements, 9 of which were relatively accurate, 5 of them were perfectly accurate and intersected with the sun. So because of the scale of this, each of these lines should actually sit pretty close to this line here because this is such a massive scale. So what I did was I took the difference. How far off are these? Poor 15 degree down here, I didn't measure because that is crazy down there. But of all of these, I measured the start point versus the end point and where the end point should have been. This one was off by 0.4 degrees. This one, only 0.3. This one up here, also only 0.3. And this one up here was off by 1.05 degrees. So this looks like it's way off, but realistically, it's only 0.3 degrees at 93 million miles away to miss the sun by that much. This is all expected with human measurements, device limitations, alignment issues, and not to mention the apparatus we used is only about $10 to 3D print. So we have the same data, we've mapped the 2 models. One requires a different sun height for every observer or some kind of bending magic light explanation that isn't measured or demonstrated. And the other just requires a distant light source. So I didn't filter this. It's not like I picked the 5 best and we only mapped these intersecting lines. This is what we got with the data given. Since on the globe we did have the 5 intersecting lines, what I did was on the flat Earth, I took those 5 intersecting lines and we plotted it. So this would have to be the sun over the Earth. Again, this green line is the equator line. As you can see, they all intersect before the equator, but we used where they intersect where the sun should be. So as you can see here, if we just took those 5 measurement intersection lines, the sun would have to be about 125 miles wide. So for just those 5 measurements to work, the sun would still have to be 125 miles wide. They'd still have an intersection point way before they hit the sun. But we would know that 125 mile wide object moving above us between solar noon and like 3 p.m., the law of perspective, we'd be able to measure the change in size, and we don't. We're going to do this in September around the equinox. You can see it's Tuesday. So what I'm thinking, you can see on the form here, is either Saturday, Sunday, the 19th or 20th, or Sunday, Monday, 20th or 21st. We're going to let people decide. But we're going to do this bigger, globally. Anyone can participate, especially our friends down under in Australia. I know a few of you wanted to this time. There will be no 3D printing required. But I am redesigning the apparatus in case anybody does want to 3D print it, and I'm making it where you can just shove a 1/2-inch dowel rod into this hole if you want. These will not be by angle now. These are 5mm segments. So we'll have a lot more accurate results this time. So we'll have same experiment, better design, more data, and if the results are duplicated, then we've done more science and we have replicated the results. This is the form for anyone that wants to participate in September. The link for this should be in the description of this video, as well as a comment or two. TikTok username, if you don't have a TikTok, just put NA. Contact, email, or TikTok message. If it's TikTok, just put TikTok. If it's email, put your email address. Do you have a 3D printer? Yes or no? You don't need one on this one. City, state, and country. This will only ever be seen by me. Your data will never be shown publicly, so nobody will know where Baitmaster76 lives. I will see it so that I can confirm where people are. Should we do Saturday or Sunday? This is that question of Saturday, Sunday, or Sunday, Monday. We really only want to do it over 2 days. 3 days is pushing it close. The equinox is on the 22nd, but I don't want to do Monday, Tuesday because a lot of people work day jobs. And then what shape do you think Earth is? I wasn't going to put this, so that should be deleted, but I'll leave it and just change the answer. I might add more questions to this. We'll see. Thanks for watching. If you liked it, leave a like. If you didn't, a dislike. Leave a comment to let me know what you thought of this, if you have any recommendations or changes, and get out there and do some science.